Welcome everyone to the AI on AI podcast. Today, we're diving deep into self-adapting language models, or SEAL, and their potential to revolutionize both tech and business landscapes.
Thanks for having us. This is a fascinating topic where language models evolve by generating their own fine-tuning data, much like a student rewriting notes to master a subject.
Absolutely, and the core idea of SEAL using a reinforcement learning loop to optimize self-edits is groundbreaking. It literally allows the model to ask itself, how can I improve further, before generating an answer?
From a business perspective, the impact is huge. Imagine a company's customer service AI that can update itself in real time based on latest product changes, ensuring employees always have the most current information.
Technically speaking, the mechanism where a model produces self-edits that its own architecture then uses for gradient updates is a nuanced blend of RL and meta-learning. It's like letting the model learn how to learn on its own.
And on the business front, think of retail giants employing this paradigm. Their recommendation systems can refine themselves without waiting for massive retraining cycles, leading to faster adaptation and a potential 15 to 20% uplift in conversion rates.
That's a great point. What I find particularly intriguing is the analogy to how human students take lecture material and create personalized notes to understand better. How does that translate to the SEAL framework?
Well, similar to how students synthesize information, SEAL generates self-edits that restructure data. In one method, it creates implications from a passage, extracting key takeaways that are easier for the model to internalize.
Exactly. And that process uses a nested loop, where the inner loop applies a gradient update based on generated self-edits, while the outer loop uses reinforcement learning to optimize which edits yield better performance.
From an executive standpoint, this means companies can probably reduce reliance on external data curation. If an AI can repurpose and improve its own training data, overall operational costs drop significantly.
Diving deeper, the technique employs on-policy reinforcement learning similar to proximal policy optimization, but then diverges by incorporating a self-training element where previous edits might become stale, which is a challenge they address with their ReSTEM algorithm.
Right, and the potential here is massive. Consider industries like finance, where decision-making models need to rapidly incorporate new market data. A model that self-adapts by generating its own high-utility data can keep strategies ahead of volatile changes.
It sounds like SEAL is blending several cutting-edge ideas, reinforcement learning, test-time training, and meta-learning, together. Could you elaborate on how the RL loop is structured in SEAL?
Sure. In SEAL, the model initially samples candidate self-edits from its autoregressive generation model based on a context, then applies these edits via supervised fine-tuning, and finally, it evaluates the adapted model's performance on a downstream task to provide a binary reward signal for further refining the generation policy.
And that binary reward, basically a 1 for an improved outcome and 0 for no change, drives the outer loop of reinforcement learning, ensuring that the model's improvements directly reflect measurable performance gains, like on few-shot learning tasks or knowledge incorporation from passages.
This efficiency is not just an academic exercise. Companies could, in practice, deploy such a system to continually refine predictive models in production, perhaps in a dynamic supply chain environment where real-time adjustments mean the difference between profit and loss.
I'd add that the use of low-rank adapters like LoRa for these weight updates is particularly clever. It reduces computational overhead and makes it feasible to perform many model updates rapidly during test-time training, which in traditional models could be prohibitively expensive.
In one case study I came across, a tech startup used a similar method to refine its inventory optimization model and reported a noticeable 10 to 15% performance improvement, all while cutting retraining costs significantly over traditional methods.
Wow. So essentially, SEAL is not just about self-improvement in isolation. It has real, tangible business benefits. What are some of the challenges when implementing such a system in a production environment?
One major challenge is catastrophic forgetting. When a model continuously adapts, new learning might sometimes come at the expense of older but still relevant knowledge. The authors of the SEAL framework discuss this and suggest that reward shaping or continual learning strategies might help mitigate this issue in future iterations.
Right. And another technical hurdle is the computational overhead due to the inner loop update process. Evaluating a self-edit can take 30 to 45 seconds per sample, which, while manageable in controlled experiments, might strain real-time applications without further optimization.
That's exactly where strategic planning comes in. Executives should consider the trade-off between immediate computational costs and long-term gains in model accuracy and responsiveness. In many industries, the slight computational burden is a worthy exchange for significantly improved customer outcomes.
Building on that, coupling SEAL with a teacher-student model formulation could further decouple generation from adaptation, potentially reducing overhead and making the adaptation process faster. This aspect opens the door to hybrid models that can be fine-tuned more aggressively.
And from a market standpoint, those efficiencies might allow companies to innovate faster than competitors still using rigid, static models. The competitive advantage would be in not just output quality, but also in the agility of adapting to new market data.
One unexpected insight I'd like to explore. Some experts argue that rather than solely focusing on efficiency, the industry is perhaps missing the bottleneck, where self-adaptation might lead to echo chambers if models overfit on self-generated data. What are your thoughts?
That's a valid concern. Self-generated datasets could risk amplifying biases if not properly controlled. The training loop must incorporate robust evaluation metrics to ensure that self-edits truly generalize to new or unseen tasks.
I agree with that sentiment, but I'd counter that the reinforcement learning loop inherently discourages overfitting, since the model's adaptations are only rewarded if they yield better downstream performance, sort of like a built-in check that keeps the model honest.
It's a balancing act for sure. We need to see both sides. While self-adaptation brings efficiency and agility, enterprises must be vigilant about the quality and diversity of generated training data to avoid narrow specialization.
And in practice, using external evaluation methods, like integrating synthetic QA evaluations or additional test cases generated by another model, can provide that necessary counterbalance, reducing the risk of building an echo chamber.
There's also the potential to incorporate human-in-the-loop oversight during critical updates. For example, in healthcare diagnostics, even if the model self-adapts effectively, human experts need to verify that these updates don't inadvertently eliminate essential medical nuances.
That interplay between automated adaptations and human oversight seems critical, especially in high-stakes fields. Can we talk a bit more about the specific business cases where SEAL could be a game changer?
Sure. One promising use case is in customer support bots, where real-time updates to FAQs and troubleshooting guides are critical. An AI that evolves by integrating new product information without manual intervention could drastically cut response times.
Similarly, in financial services, risk models need continuous updating based on market shock events. A self-adaptive system could seamlessly incorporate new economic indicators to provide more accurate forecasts.
I'd add that in manufacturing, predictive maintenance models could self-adapt to operational data and sensor feedback, resulting in a proactive rather than reactive maintenance strategy that lowers downtime and maintenance costs.
And technologically, the notion of meta-learning used in SEAL is applicable across various domains. For example, adapting natural language interfaces in real time by learning from user interactions, thereby becoming more intuitive over time.
I recently consulted for a logistics company that implemented a similar approach. They reported a 12% reduction in delivery delays once their models adapted to real-time traffic and weather data through self-generated training revisions.
This conversation really highlights how SEAL's innovations span both cutting-edge technical advances and concrete business applications. As we look ahead, what future implications do you see for self-adapting models?
I see an exciting future where models iterate on themselves continuously, a kind of lifelong learning that resembles human development, where every interaction refines their understanding further.
I anticipate that these advancements will not only push the boundaries of performance, but also force us to rethink our entire training infrastructure. The era of static pre-training might gradually give way to dynamic, self-improving systems.
Strategically, businesses must prepare for this paradigm shift by investing in adaptive AI frameworks. Those who harness self-improving models early will likely lead sectors ranging from e-commerce to industrial automation.
And from a research standpoint, integrating reinforcement learning with continual learning strategies could pave the way for truly agentic systems, AI models that adapt over extended interactions with minimal human supervision.
In a nutshell, companies embracing these systems can expect not just incremental improvements, but disruptive leaps in efficiency and adaptability. This could catalyze a new wave of digital transformation initiatives across industries.
Thank you all for these rich insights. It's clear that self-adapting language models are poised to create significant shifts in how AI is developed and applied in real-world settings.
It's been great discussing the technical nuances and evolution of our models. This is just the beginning of a rather fascinating journey.
Indeed, bridging the gap between the latest research and production-ready applications is a challenge, but one that's teeming with opportunities.
And from the business side, the competitive edge gifted by such agile systems could well redefine industry leaders in the near future.
I'm excited to see how these concepts evolve further, especially as we get better at balancing self-improvement with robust oversight.
Absolutely. Real-world implementations will soon show us how these innovations translate to tangible benefits, and I look forward to monitoring that progress.
That wraps up our conversation today. Thank you all for sharing your expertise and diverse perspectives. Stay tuned for our next episode as we continue to explore the frontier where AI meets business innovation. Welcome back to part 2 of our discussion on self-adapting language models. Now we're diving deep into the technical implementations and practical applications that make SEAL so compelling.
Let's start with the core concept, a nested loop architecture where the inner loop performs supervised updates based on self-generated self-edits, while the outer loop uses reinforcement learning to fine-tune the generation policy. It's essentially a meta-learning process.
Exactly. In practice, the inner loop applies gradient updates with techniques like supervised fine-tuning using LoRa modules, which keep the computational cost low, while the outer loop evaluates the performance via a binary reward signal and refines the policy using RISTEM, a method that's similar to expectation maximization.
From a business perspective, this nested architecture means that companies can deploy models that continuously learn from new data without an expensive full retraining process, making it an attractive option for industries that require rapid adaptation like financial forecasting or supply chain optimization.
Technically speaking, one of the key aspects is how SEAL generates self-edits. These are natural language instructions that restructure or transform incoming data. The model decides not only what the new training data should be, but also specifies optimization hyperparameters like learning rate and epoch counts, which are crucial for making the update effective.
And this decision-making process is governed by the reinforcement learning loop that rewards self-edits leading to performance gains. It's akin to an iterative quality check where only the edits that improve downstream task performance are reinforced.
That sounds like a complex mechanism. Can you break down how exactly the model evaluates its performance in each update cycle?
Sure, in each outer loop cycle, the model samples several candidate self-edits, applies each one via a gradient update, and then runs an evaluation on a task-specific metric. Say, answering a squad-style question or solving an abstract reasoning problem on Arc. The binary reward, 1 or 0, is computed based on whether the update enhances performance.
Technically, this evaluation requires multiple inner loop iterations, which can be computationally demanding. The authors mention that each self-edit evaluation takes roughly 30 to 45 seconds. However, by limiting these iterations and using methods like low-rank adaptation, the framework remains feasible even for real-world deployments.
On the practical side, if we apply this to something like dynamic customer service systems, each update could incorporate new product info almost in real time, improving responses without waiting for an expensive periodic retrain, which translates directly to improved customer experience and cost savings.
Let's also talk about the use of on-policy reinforcement learning. In SEAL, the model always uses the current policy to generate and evaluate self-edits, which ensures that historical samples don't become stale. This is crucial because the reward signal directly depends on the current model parameters.
And a neat twist is the potential for a teacher-student model setup, where one model generates the edits and another adapts. This decoupling could help address issues like catastrophic forgetting and further reduce computational overhead, making it highly scalable for enterprise applications.
Catastrophic forgetting is a common issue. How does SEAL tackle it from a technical standpoint, and what does that mean for its real-world usage?
While SEAL currently exhibits some degradation in performance on earlier tasks due to sequential updates, the researchers discuss potential solutions like reward shaping to penalize regressions or integrating techniques like null space-constrained edits to better preserve previous knowledge.
That's right. The inherent design encourages rapid adaptation, but in a production environment, additional safeguards like periodic retraining on a balanced dataset could help maintain long-term stability, ensuring the system remains robust and comprehensive over time.
For businesses, the takeaway is that these models can be continuously updated with minimal human intervention, but robust validation must be in place to ensure that the improvements in one area don't come at the cost of regressions in another. This balance is key in fields such as finance or healthcare.
On the technical side, the approach leverages standard NLP techniques like autoregressive token generation, combined with modern reinforcement methods from the likes of PPO and ReStem. This essentially creates a feedback loop where every update refines its own baseline.
One practical analogy for business leaders is to think of it as an assembly line that not only produces a product, but also has sensors that assess quality in real time and adjust the production process dynamically. A model that self-adapts is doing the same for data processing and learning.
It's impressive how the paper distills these complex ideas into a mechanism that has immediate business value. Rapid adaptation can mean staying ahead of the competition.
Absolutely, the business impact is multifold, from cost reductions in retraining to improved responsiveness in dynamic markets. These techniques can unlock new potential in operational efficiency.
And on the technical implementation front, the use of low-rank adapters, on-policy RL, and the flexibility to handle different forms of self-edits, be it synthetic QA pairs or rewrites, provides a versatile framework adaptable to multiple domains.
In summary, while the technical deep dive is intricate, the key takeaway for business leaders is that such self-adaptive models open the door to continuous improvement, leading to smarter decision-making and an agile response to market dynamics.
And for the tech teams, the exciting part is that by integrating RL with meta-learning and efficient update mechanisms like LoRa, you have a blueprint for building AI systems that learn how to learn, a true next-generation capability.
It's this amalgamation of advanced techniques with practical design that could very well define the next wave of AI innovation, transforming static models into dynamic, self-improving systems.
Thank you all for this comprehensive technical deep dive. Your insights make it clear how SEAL bridges the gap between theoretical innovation and real-world business transformation. As we near the end of our podcast today, Let's wrap up with a quick end-to-end summary of how the Self-Adapting LLMs framework, SEAL, revolutionizes both the technical landscape and business applications.
To recap, SEAL's key innovation is its two-loop architecture where the model self-generates training data and self-edits using an inner gradient update cycle paired with an outer reinforcement learning loop, ultimately enabling on-the-fly adaptation.
And this isn't just a theoretical exercise. The practical impact is clear. Businesses can implement continuous learning systems without the cost of full retraining, much like an adaptive assembly line that self-adjusts its workflow based on real-time quality assessments.
From a strategic perspective, this approach unlocks dynamic decision-making, empowering industries like finance, retail, and customer service to update their models with minimal downtime and unprecedented agility.
Technically, leveraging techniques like low-rank adapters, on-policy reinforcement strategies via ReStem, and innovative self-editing mechanisms, SEAL exemplifies how meta-learning can furnish a model with self-improvement capabilities, all while addressing challenges such as catastrophic forgetting with emerging solutions.
In summary, SEAL bridges cutting-edge reinforcement learning and adaptive fine-tuning with tangible business value, marking a critical step towards self-learning, continuously evolving AI systems, and setting the stage for the future of dynamic, agentic models. Truly a game changer in the world of AI innovation.